Okay, hello everyone. We're here today to talk about some of the code size improvement work that we've been doing in TCWG over the past Connect cycle, the past 6 months. So today we've got the work of 3 people being presented. There's myself, Peter Smith, my colleague Oliver Stannard will be talking about his work in the middle. The third bit of work is by our colleague Ivan Roux. Unfortunately can't be here today, but I'll be presenting his slides on that basis. Okay, so what are we actually going to be covering today? We've got my investigation in embedded code size of GCC versus Clang. We've got Oliver's work on virtual function elimination, and then we've got Ivan Roux's work on function outlining. So we'll be roughly splitting the presentation into 3 thirds, starting with mine. Okay, so a whole load of material on the slide there. This is sort of, I'll sort of summarize that here. So what we're effectively looking at here is how do GCC and Clang compare on typical embedded systems code? So we weren't necessarily interested in sort of finding some typical benchmarks. It's actually quite difficult to find representative code for embedded systems to actually check. So in the end we chose Zephyr because that was being highly associated with Linaro in the light group. And we chose that for integer-based code. There's all sorts of bit twiddling, sort of inline assembly in Zephyr. And for sort of floating point code generation, for the sort of Cortex M4 with a floating point unit, we chose CMSys DSP. We wanted to compare the best of what GCC could do with the best of what Clang can do. So we took the trunk builds from on the day that we actually did the investigation. Yeah, primary goal to find out just how Clang is compared to GCC. Secondary goal, any sort of things we found along the way in the analysis that we could perhaps fix up later, we would record that. Okay, so for Zephyr, Zephyr is actually a library. So it's actually quite difficult to say measure the code size of just Zephyr. Really, it's you include whatever you use when you build your application. So what we used was the sample code that came with Zephyr. There's well, I don't know, tens of examples that come. Some of them are networking, some of them threading, some of them Bluetooth, that type of thing. So what we did is we sort of basically built as many as we could to sort of try and get the executable or the code size of the executable rather than just objects. So for GCC, we used a TCWG built ARM non-EABI GCC with GNU RM libraries. For Clang, we built a Clang installation, but we were going to use GCC as the linker driver. So that meant that all of the linking side would be the same between GCC and Clang. So we're not comparing the whole LLVM toolchain versus the GCC toolchain, just the code generation aspects of GCC and Clang. Okay, right. So we wanted to measure the size of the executable wherever possible because there are aspects of code size that get altered at link time, things like duplicate information that can get merged into one. There's library code that gets dragged in. The structure of how the compiler generates code can affect garbage collection, that type of thing. And we'd also want to make sure that the binary libraries are the same. So we're using the size of the text section as a proxy for the code size. That's not perfect in all cases, but for Zephyr, it worked reasonably well. It basically how the memory layout was done in Zephyr. And for the symbol, the code size of a particular function, we use the ELF symbol size. That's just a little bit of methodology. So moving on to the results. So first thing you'll notice about this graph, if you can see it from there, is that the scale on the y-axis is heavily compressed. So normally when that's a warning sign whenever you see somebody in marketing do that, because it's normally a way of distorting a graph. But if I didn't do that, then you'd end up with something that was hardly noticeable at the distance there. But yeah, in effect, you can see things range from Clang being 1.5% behind. Just to explain, the red line there is GCC. We basically normalized all of the GCC to 1.0. So basically the blue is what Clang is as a sort of relative to GCC. So in the threads example, Clang was 1.05 times bigger, and towards the end, maybe Clang generated some that were 98% of the size. But overall, LLVM came out about 1.1% larger overall, which is actually relatively close. Certainly, Clang's caught up a long way over the past few years. There were at times where GCC could be about 10% better. So a lot of work has been done in that area. So yeah, we did Cortex-M4 and Cortex-M0, Cortex-M4, Thumb 2, Cortex-M0, Thumb 1. So there are definitely code generation challenges at Thumb 1 only. So for Cortex-M0, we'll notice that GCC does better still here. A lot more of the peak differences are very much the same, but more applications, so larger code differences there. So the Cortex-M0 has fewer supported samples, because a lot of times when you build a Zephyr sample, it'll be a particular board that you build it for, and that board has drivers, that type of thing. So we've got a different sort of set of applications for M0. But yeah, ended up Clang LLVM being about nearly 3% larger in that case. Okay, so a brief analysis of the results. We have gone through these in detail. Unfortunately, the time that we've got here, we can't go through all of them. It's generally a lot of little things. Unfortunately, when you do performance benchmarking, you often have hot loops where you can make a change in a hot loop that might take up, say, 80% of the runtime. So you can actually make a small change and make a large difference. Code size is the whole program. So it's very much a lot of little things multiplied over the whole code base rather than one big thing. But yeah, in general, to look at that, one of the theories I had was that that Clang might be using an awful lot more library code, but it turns out that the amount of library code is less than 1%, so not really any much of a difference there. Other theory I had was that, well, if Zephyr is a library, then we might just be dragging in the whole thing all the time, and when I'm just measuring the same thing over and over again and not really getting the differences. It turns out that the bit of Zephyr that was common to everything was only 5% of the largest example. So this was kind of, I think these code size figures were representative of the whole thing rather than just on one particular bit there. So we also found turning off inlining halved the difference, which implies that GCC's got a better inlining strategy there. And looked also like the register allocation was better in GCC. But in general, lots of little things. If you're interested in the details, by all means, come and talk to us afterwards, and we can go through those. Okay, I'm going to go through this a bit more quickly. Siemsys DSP. This is a library from ARM. It's basically implementations of common DSP functions. Now, there wasn't a set of samples that I could build here, so I basically just measured the code size of the object files. But in the way that the DSP library is structured, that works quite well, because it's basically one function per source file, and it doesn't cross-call amongst the things, so this worked quite well. And in this case, Clang actually did an awful lot better. It was actually 90% of the size of GCC on Cortex-M4. We decided not to use Cortex-M4 with a floating point unit here, and there's no M0 with a floating point unit, so we haven't got M0 figures here. But yes, as you could see, Clang did significantly better at this than in Zephyr. So some analysis of results there. The actual looking at the generated code, it's DSP code. I'm not a DSP guy. It was very difficult to actually understand what was coming out at the end. There were a few things that I spotted, recorded. Clang makes better use of the rounding instructions, so that's a common idiom in DSP code, is to basically round up to the next value. Clang could recognize that and use the rounding instructions in the instruction set. And actually, when I say GCC inlines this long shift left, I think a more accurate way of saying that is that Clang could recognize a long shift left and call a library function rather than generating all the code for it, that type of thing. So yeah, there was a few things there. So I'll conclude there on the code size investigations. GCC is an average smaller than Clang for integer type of code. But Clang is getting better. Cortex-M4 closer than M0. Clang's better at the DSP code. We've recorded the specific issues, and we'll go from there. So now I'm going to hand over to my colleague Oliver for his work on function elimination.
Hi, so I'm now going to talk about one of the optimizations I've been working on in LLVM, which is removal of dead virtual functions. So this is an example of some code that we'd like to be able to optimize. You've got a C++ struct with two virtual functions, a second one which inherits from it and overrides them both. we've got some calls down here through two different pointer types. The first one is through the base class type, so it could at runtime go to either of the implementations. The second one is through the derived class pointer type, so it could only possibly go to B's implementation. So we have one function up there that can't possibly be called, assuming this is the entire program. But the compiler can't currently recognize this. And this is why. So this is what it looks like to global dead code elimination, which is the LLVM pass we'd normally expect to be able to remove completely unused functions, global variables, that sort of thing. So you've got two constructors for the two classes, which take the addresses of each class's vtable, which contain pointers to every virtual function. And then separately, we've got the call sites, which don't have any references to anything. They work purely by loading the pointer to the vtable from the object, loading the pointer to the virtual function from that vtable and calling that. So they don't know at compile time where they could be going. And this means all the virtual functions are referenced by something. We don't know just from this that it's safe to remove any of them. So LLVM has something that could help us with this. This is type metadata, which is optionally added by Clang to vtables and virtual call sites, which can give us this link between the call sites and the virtual functions they could possibly end up calling. Currently this is used for another optimization called devirtualization and for the control flow integrity security checks. And with some small changes, we can use this to do virtual function elimination. So I won't go through this in detail, but these are the virtual table of global variables with extra type annotations on the end. And this is a snippet of a call, which uses this LLVM type checked loads intrinsic function, which sort of attaches the extra metadata that allows us to make this link. So now we can modify the global DCE pass to ignore the links going out from, ignore the references from the vtable to the functions. We can use the type metadata to reconstruct the possible call targets of each site. So we had that first function through the base class pointer that could go to either implementation, and we have that second call site that we now know can only reach one of the implementations. The result is A bar is not referenced by anything, and the optimization can remove it. So this isn't always going to be valid. We need to see every call, we need to know that we can see every call site that could possibly go through this class, which in general means you need to build with hidden visibility and with LTO. It can also work on classes in anonymous namespaces, but there's not going to be much dead code there. There are some more complicated classes. There is an attribute you can change the visibility per class. That makes things a bit more complicated because a call could go through a more visible base class. So I've had to add a new bit of metadata vcall visibility to represent this in the IR because it's not otherwise sort of represented there. So I've got some benchmarks for this. So this is the C++ subset of spec, the baseline being maximally optimizing for code size, LTO, and visibility hidden, so all the conditions for this optimization to be valid, but without it turned on. And this is the code size change when you turn it on. So we've got a few pretty big wins. Zalank in particular is a big C++ code base, so there must be a lot of code in there that's not used. Obviously, some of the sub-benchmarks, there's not much change. There's not much dead code to remove, and this won't affect the C or Fortran sub-benchmarks at all. And this is the results on EmbedOS, which is a similar real-time operating system to Zephyr, but written in C++. And again, we see things like sockets and mesh minimal that are larger applications using file system networking libraries that have a reasonable amount of stuff that we can remove. So currently this patch is in review. Once this is committed, hopefully we can get it tested and turned on by default. There's some possible future expansions It currently requires full LTO, so it's not good for very large programs where that's not practical. It might be possible to get it working with thin LTO in a similar way to devirtualization can do that now. And it might also be possible to extend it to eliminate dead runtime type information that would require extra annotations in Clang to note places where types are used for exceptions, dynamic casts, that sort of thing. So now I'll hand back to Peter to talk about Ivan's work on the machine outliner.
Okay. Right, so the machine outliner is a code size reduction pass. It's basically when a function inliner is taking a function and but it's outside, well, when a function is called, an inline is where you take the body of that function and you move that into the actual place where it's called. So you basically don't get the overhead of calling the function. Function outlining is kind of like the reverse of that process. It looks for common bits between functions and sort of says, okay, well, this bit of code is common in all of these different functions. Why not I make a function out of it and call that function from the call side? So it's kind of like the reverse of inlining. So this was introduced by Apple for AART64 and x86, and Yvonne has been porting that to ARM, Thumb, and Thumb 2. Okay, so here's an example here. So yeah, see if you can spot the difference at this particular point. There is another box that come on the slide that we'll show you here. But as far as I could tell, this is A plus B plus C plus D on the left side, and A plus B plus C minus D on the right-hand side. And you can see when in the next slide, yeah, this is the common bit at the top in the sort of slightly less grey box, and the bit at the bottom, add and sub. So what the function outliner does is pull all of that common code into a separate function and call it. So here we go there. The only real difference is at the call site is we've had to save and restore the link register, and then we've just replaced all of that bit of code with a branch and link to the actual code on the right-hand side. And we've done that here in bar as well. And we've saved about 28 bytes of code in this particular process. Okay, so that's it in a nutshell. There's obviously an awful lot of complication behind the scenes. And there's also an awful lot of cases where the outliner can't work. So conditional execution in IT blocks, my understanding from Yvonne is that you can outline code that contains conditional execution in IT blocks, but nothing that crosses the boundary, because obviously when you do a branch and link, the linker might intercept that call and you might get the information wiped out of that particular case. Again, IP register, the linker might use that, so, and same with condition codes. Obviously, if you've got an instruction that has when I say PC-dependent behavior, if you're doing a PC relative load and you move it somewhere else, that load from the PC is going to be somewhere different to where you expect it. There might be some cases where a very smart outliner might be able to fix that up, but for the moment it just says, no, not going to do it. Stack operations as well. My understanding from Yvonne is that if we look back to this example here, you'll notice that there's no difference in the register allocation at all. In theory, you could say, well, okay, in the outline function, you could restore registers, but the outliner doesn't do that. It looks for things that are pretty much just identical, so you keep the overhead at the calling function low. Okay, so here's some results with the outliner. So there's quite a few of these. I'll go through these fairly quickly. So spec 2K6 on ARM, we're getting about 5% reduction across the board on that. That's pretty much what Apple was seeing with AART64, so that's a pretty good result. Thumb mode is showing smaller improvements. At the moment, Yvonne thinks this may be down to when you use OZ, you use more PC relative loads from constant pools, and these are harder to outline than the MOV-T, MOV-W case that we had earlier. But there's some further work to go on there. Okay, so LLV MCT Mark is a subset of the LLVM nightly test suite that's done for code size, and we see one of them, that KC, shows a huge, well, I say huge, it's about, again, we've got to be careful of the scales here. That's not 0, that's 0.75, but it's showing about 25% reduction in size there, so that's showing quite a lot of improvements there. Okay, Thumb again showing smaller improvements than ARM. Okay, so here's the same thing run on Zephyr. So what we're doing here is comparing the Zephyr Clang to Clang. So beforehand, Clang 1.0 is Clang with OZ, the same sort of flags I was using earlier. And with the outliner, we get on average about 1.1% smaller. So yeah, not as great a result as we had before. This may be due to the structure of the Zephyr code base, as opposed to, say, something more like a typical application in spec. But given that we said before on Cortex-M4 there was about a 1% difference, so kind of with the outliner, Clang should be coming in on a par, at least with V7M with GCC on Zephyr, with the outliner. Okay, so summary there, Clang's slightly worse, this is the summary of the whole presentation here. So Clang is slightly worse than GCC for code size on the Zephyr code base, about 1%. That's probably within the range that you might consider experimenting with Clang, certainly if you think that there are other things there with Clang. We think that that gap can be closed. Clang can be substantially better at DSP and floating point code generation. So if your example has large amounts of DSP-like code, I'd say certainly give Clang a shot and see what sort of things come out for your code at that point. We're hoping to close some of that gap with forthcoming size optimizations to Clang, such as virtual functional elimination and the outliner. Okay, that's all I had. So we've got a few minutes for questions. There's a microphone over there. And Oliver better come up here, so just in case.
Hi, did you measure any performance improvement with these smaller builds?
No, we didn't track performance, mostly because we were doing embedded code, and we didn't really have the means to actually run. They were mostly things like send a network packet to something that didn't exist on. We really needed the development board to do it, so we didn't really have the means to actually do that. But it is certainly worth. I imagine virtual functional elimination is not going to have any impact on performance. We're just removing dead stuff. But certainly outlining might have a performance impact at that particular point.
Yeah, if it makes it a bit nicer to the cache or something.
Yeah.
So for the virtual function elimination, right, is there any reason why devirtualization was not doing the case you were? I thought like devirtualization was supposed to handle those cases, right?
So devirtualization is kind of the equal but opposite optimization. So devirtualization is when one call site can be proven to definitely go to one target.
Basically, virtual calls becomes direct calls, right?
But the conditions for virtual function elimination are slightly different.
Okay, I'll talk to you probably later.
I just wanted to say Jessica's work on the outliner for ARch64 is one of the most exciting code size optimizations in LLVM, and I'm really grateful to Lenaro for bringing it to the ARM port as well.
How are we doing for time? Just so I think we've got probably close.
7 minutes.